So again, before, in chapter 2, what we could say is, well, if you know a certain amount of hydrogen gas, you can find how many molecules that there are. So again, if we go back to that picture, we knew if you have a certain mass of the hydrogen gas, you can go to moles and then you can go to molecules. So that's what we already did. And this is just a reminder if you've forgotten how to do it. So we've got our grams, and then we do grams in 1 mole, and remember that's the molar mass, and it's from the periodic chart. And then over here we have Avogadro's number. Remember, that's how many molecules are in a mole of something. So you've done that before. But here's what we haven't done. If we know how many moles of hydrogen gas we're using, how many molecules of oxygen will it take? So this is going back to the equation up here. We're going between hydrogen and oxygen. So now what we're wanting you to do visually, I'm going to change colors. I'll go to dark blue. So we have this guy. We're going to go to molar mass, but now we're asking you to move to the other guy. And I should have made this arrow going down because the question asks about particles. But most of the time what you're doing in this chapter is the picture that I drew. We got our grams of hydrogen, and we turn those into moles using the molar mass just like above. And then notice my units here, like I'm doing the unit match, so I'm writing grams in 1 mole. And in a mole, this is the key bit. You can go from moles of one thing to moles of the other using coefficients. This was right here, that's 1 to 2. 1 to 2. And all the rest of the math, it's what you've done before. So in a sense, it's not really that you're doing anything new in this section of the chapter, but we're reminding you how to do grams of moles to molecules, or moles to something else. But the something else is what's new. This is the only new thing, and it's just letting you know that, hey, you can use the coefficients to move from one part of the reaction to another part of the reaction. In this case, we went from one reactant to another reactant. You can also move from a reactant to a product, or even from one product amount to another product amount. This is how much oxygen you need for the reaction. Now, if we were changing it into molecules of water, so here's our water. If we were changing it into molecules of water, I don't know if you can see that it's 2 to 2. So the thing that would change would be that this number becomes a 1. Nothing else would change. I would change this to water, and this would become water, and this would become water. But notice that the numbers aren't going to change, so it's just half of that number. So 4.62 times 10 to the 1/3 divided by 2 is 2.31. So I could have also converted into water, and I would have said that I would have made 2.31 times 10 to the 23rd molecules of water are made. Erase that so you're not losing that all over the place. Yep. Okay, so right here, this is the theoretical yield. This is the thing that if the world were perfect, and if I didn't get something wet and forgot to dry it, and if all of the reactants were completely pure, and if my scale weighed to the 100th degree, and if my glassware was perfectly pure, and if I did every step as a perfect person, and there were everything that makes the reaction want to go was in place, I would get that many molecules. So in real life, you don't actually ever reach your theoretical yield. And if you do and you try to write a paper on it, people are going to be suspicious. So you don't want to get your theoretical yield. You want to get close to it. 90s is real nice, something in the 90s.